telling you where I first heard David Clark's name. I was a graduate student pursuing a master's degree at Emory University in Atlanta, Georgia in the late 80s. And they had a rule there, if you were pursuing your doctorate, 4 years of funding. So from whenever you came in, bachelor's only, master's, whatever it was, you had exactly 4 years of funding, after which you went elsewhere if you didn't have a PhD. And of course, in the third year, as people are working on their doctoral dissertations in a panic to come up with that original new result, there was always discussion about, am I going to finish in 4 years or not? And without fail, some graduate student always said, it shouldn't be a problem. Back in the late 60s, there was a fellow named David Clark that finished in 2. And furthermore, that was after 3 years as an undergraduate. So it only takes 5 years to get from high school to a PhD in mathematics. That's the moral of that story. And so 20 years later, I was at a conference and talking about inquiry-based learning in mathematics and the teaching of mathematics, and a gentleman strolled into the room and we started talking, and I introduced myself, and he said, well, I'm David Clark. I stepped back, I said, you're David Clark? I said, well, that sounds like a common name. You didn't happen to attend graduate school at Emory University? He said, well, I did. And so then I learned that it was, in fact, the infamous David Clark of my graduate school days. David Clark took his bachelor's at Emory University in '67. He took his doctorate at Emory University in '69. Since that time, he has primarily been at New Paltz. However, he has spent a year at numerous institutions: Georgia Tech, the Humboldt Foundation in Germany, the New York College in Athens, Greece, the University of Waterloo in Canada, the University of Lisbon in Portugal, La Trobe in Australia, and Oxford University. He also serves currently as submissions editor on the Journal of Inquiry-Based Learning in Mathematics, something that he and I co-founded, and he is here 2 weeks, hosted by Lamar University in the mathematics department, where I've managed to engage him in 4 different obligations, as well as working together. So it is with great pleasure that I introduce David Clark.
Thank you, Ted. It's very nice to be here. It's a nice opportunity to come and work with Ted and meet everyone here. I thank you for coming out this evening. I know everybody has other things to do, but I really enjoy talking about the things that excite me to people from all disciplines who might be interested. So tonight what I want to talk about is actually a topic in physics. I want to talk about quantum theory. And so this is something that I consider to be one of the most exciting and profound discoveries in science of the 20th century. And it struck me that lots of people hear about it, and yet few people really understand what it is. And what particularly amused me is that the essential ideas behind it are really quite accessible to interested people, to a general audience. And generally people think that in order to understand anything about quantum theory that they would have to study this for many years, and that they probably aren't going to do that. But you really can get an idea of what the essential and interesting issue is behind it in a fairly short time. And so I'd like to give you some kind of insight into that. So what this is about is physics. And so I want to start by talking a little bit about just some informal physics. Imagine that someone hits a baseball, and the baseball goes up, and it's hit right here, and it goes up like this, and there's a certain kind of informal physics that gets used by maybe the outfielder who's standing over here and wants to try to catch the ball, and the outfielder looks up and he sees the ball hit and sees which way it goes and how fast it's going, and makes some kind of judgment about where it's going to be a couple of seconds later. And his best guess might be that it's going to be right there. But of course, he doesn't really know that it's going to be right there. He just sort of has a rough idea of where it's going to be 2 seconds later. He might think that, well, I'm positive it's going to be somewhere in this region. And maybe it's got a 50% chance of being in this region, and a 10% chance of being in that region, and maybe 1% chance of being over there. So the ball's coming up, and he sort of has a rough idea of where it will be in 2 seconds and where it's going to come down. And based on that, he goes to where he thinks it's most likely to be to come down, but with the idea that it might be over there and it might be over here. So it's sort of, in his mind, it's sort of a probability distribution about where that ball is going to go. And he bases his actions on that. Well, now, we might say to this outfielder, well, you ought to study a little physics, because if you know the exact speed and direction of the ball when it's hit, then you can use some freshman physics and calculate exactly where it's going to be at a particular time t later. So just our basic physics, classical physics, would allow you to calculate just where the ball will be 2 seconds later. So you just need to learn a little physics, and it will really help you out a lot. Well, this is, of course, what people do. They use physics to figure out how things will move and what will happen with them. But about 100 years ago, a little over, people started trying to do this with subatomic particles. And so you could do the same kind of thing. Imagine you have an electron. So here's an electron, and the electron is shot up like this, and say you have a positive plate down here that's going to attract it and bend it back down. And now you want to know, where will the electron be 2 milliseconds later? And so you do the calculation just like you would if it was a baseball. And you say, well, I think it should be right there. And so then you do an experiment to see if your calculation is right. And when you do the experiment, you see where you put a detector there to see where the electron will be 2 milliseconds later, and you find it right there. Well, that's pretty good, but it's not exactly right. So you go back and tune up your equipment and try it again, and it's right there. Well, that's not really any better, close, but not exactly right. And so you say, well, you go to the chairman and say, well, I need some money to get some better equipment. And so you go get some better equipment, and you get it all tuned up, and you try it again, and it's right there. And you're sure that the equipment is good, that there's no error in the equipment, that the electron just isn't coming out to be where you calculate it to be. And you do this over and over, many times, and you record where the electron is each time. And you get a distribution that looks maybe something like that. And what you find is that if you shoot the electron again, where is it going to be? Well, you have a calculated position right in there, but from your experiment you say, well, I'm almost certain it's going to be somewhere in here. It's got a 50% chance of being maybe in here, and a 10% chance right in there, and maybe only 1% chance of being over here. So what you have is sort of a probability distribution, just like the baseball player has, about where it's going to be. It turns out 100 or so years ago, when people started looking carefully at this, that this is the way they found elementary particles behaving. That the calculations they did didn't give them the exact answers that they would expect, but they would get a spread like this. And so they developed a theory that's called quantum theory, which describes the behavior of an electron in terms of this kind of probability. So what quantum theory would tell you, if you have an electron and you shoot it up like this, and you say, where will it be in 2 milliseconds? What quantum theory will tell you, it will not give you an exact position. Like classical physics gives you an exact position for the baseball. What it gives you is a probability distribution. Quantum physics will tell you, after 2 milliseconds, it will tell you the probability of that electron being in any region you like. You specify the region, it will tell you the probability it will be in there. And that probability distribution sort of looks like what's drawn there. That's where you're likely to find it. It doesn't tell you exactly where it will be, it just gives you a probability distribution about where it's likely to be. Now, what happens is there is a difference between baseballs and electrons. One difference is that when you play baseball, you usually use one ball. But when you use electrons, you usually use a lot of them. Okay? So what's going through this wire is trillions of electrons. And if you have a fluorescent tube, you've got trillions of electrons going through it. So in practice, when we shoot some electrons somewhere for some reason, we're not shooting one electron, we're shooting a stream of them. And so if you shoot a whole bunch of electrons up like this, and you say, well, where will they be after 2 milliseconds? Well, they'll be distributed like this, just like that picture. They'll be spread out in a distribution that's exactly what quantum theory gives you. The distribution, the probability distribution of where any particular one would be, describes the actual distribution of a whole bunch of them. And since we're primarily interested in a whole bunch of them, you just don't get much out of a wire that has one electron going through it. You're always using trillions of electrons at once. Quantum theory is perfectly adequate for all of the electronics and all of the electronics industry that's developed in the last 100 years has been based on it, and it works very well. And everybody's happy with it. And quantum theory will describe this distribution as a function of time. So if you give me a time, you give me the initial, you give me a time and a position, probability will give you quantum theory will give you a probability of finding it in that position, or in a region. And so it looks something like this, that after maybe 1 millisecond, the distribution would look like this. After 2, like this. After 3, and after 4. So the description, that description is giving the probability distribution for each time. And it just looks like a wave moving across over that arc. And so in terms of quantum theory, the electron is actually described as a wave coming across like that, rather than as a single particle. And this is this wave-particle duality. And so this gives a nice description of how electrons will behave, and this has worked to do everything that we needed to be done, and so everybody was very happy with this. And that might have been the end of the story, but there was one fella who wasn't happy with it. That was this guy. So this is Einstein. And Einstein was involved in the inception, well, he created relativity theory, but he was also involved in the inception of quantum theory as well. He was part of that team. And he looked at this and he said, well, this is nice that it works so well, but really I'd like to know if you have just one electron, where is it after 2 milliseconds? It's got to be somewhere. Where is it? And quantum theory isn't telling me where it is. Quantum theory just says how likely I might find it here or there. And so I'm no better off than the outfielder in the baseball game. I'd like to know where it really is. I'd like some kind of physics that would tell me where it really is. So he's not objecting that quantum theory isn't correct. The distribution is correct. It's just not giving you the whole story. As he said, it's not complete. And so what he said is that surely the electron, a position, is a real inherent predetermined property of the electron. The electron is really somewhere. And so quantum theory is just incomplete. It's not telling you everything. It's not telling you exactly where it is. And we should try to find a complete theory that will tell us where it really is. Well, that seems all very reasonable, but what happened was that the quantum theorists didn't quite buy into that argument. What they said, and this was the part of the great debates between Bohr and Einstein in Copenhagen in the 20s, where the quantum theorists argued that no, it doesn't really have any predetermined position. It doesn't have a real position until you measure it. Until you detect it, it is just this probability distribution. It doesn't have any real location in space until you locate it. And theory is really just telling you all there is to know. And essentially they said that that might seem strange, but you just have to get used to it. Well, so Einstein wasn't very happy about that. And he was interested in finding some way to get a better theory, or in this case, just convince them that there must be a better theory. And so what I'm going to talk about is his quest to do that. And now it turns out that if you look at the position of a particle like an electron, well, the position is given by 3 coordinates. And each coordinate is a number, which is a decimal expansion. So that's sort of a complicated thing to talk about. And so what we're going to do is talk about a much simpler property of these particles. It's not a familiar property, but it's a simple one, because it's a property that doesn't have some complicated values. It's a property that the particle either has or doesn't have. So what we want to know is whether it has this property or it doesn't. There's only two possibilities. And so I want to describe what this property is. And the particles I'm talking about for this lecture are, I'm going to talk about electrons and also positrons. A positron is a particle that has it's a particle of antimatter, and it has the same mass as an electron, but it has a positive charge. And there really do exist such things, but they don't hang around for long, because if a positron collides with electron, then they annihilate each other and just turn into energy. And so we don't see many of them around, but in laboratories they can be produced. So I'm going to talk about these 2 kinds of particles, an electron and a positron. When I say particle, I mean one of those, and those are the only ones I'll talk about now. But what I say has analogs for other elementary particles as well. And the property I want to talk about is what we call spin. And we call it spin because it behaves in a way that's analogous to a ball spinning. But the electron really isn't a ball, and it doesn't really spin, but it has a property that's analogous to spinning. And so it is called spin. And it can be described like this. If you designate a direction, so alpha is an arrow that indicates a direction, then you can talk about spinning in the alpha direction. So if you had a ball spinning in this direction, it would mean that its axis is rotating along that arrow. That would be a ball spinning with that angular momentum. And so spin can be described by an arrow along the axis of the spin for macroscopic objects. And so with these elementary particles, if you take a direction, alpha there, then we can ask, does the electron have alpha spin? And I sort of think of that as meaning that, well, this is the way I like to think of it, but this is off the record, that alpha goes like this. And so imagine that the electron's really spinning, and its axis is somewhere like this. Well, then I sort of think of it that it has alpha spin if its axis of spin is pointing up on the alpha direction. And it doesn't if it's pointing down somewhere in the other direction. So then I can say it does have it or it doesn't have it. That's a way of thinking of it. Okay? Now that's off the record. So on the record, this is what happens. That you can build a little box that will test the particle. So here's a particle, one or the other. You shoot it into the box, and it's going to tell you yes or no if the particle has alpha spin. Okay? Now, we don't really know what alpha spin means, and that's okay. I don't know what it really means. I don't think anyone really knows what it really means, but it doesn't matter. All we need to know is you can build a little box so that you can shoot the electron into that box, and it will tell you yes or no if the particle has alpha spin. So either a green light will go on saying yes, it has alpha spin, or the red light will go on saying no, it doesn't have alpha spin. Okay? So that's all there is to know about spin. Now, so this is, what's nice here is that this is a simple property of the particle, a much simpler property than its position or its velocity, which involves several numbers. It just either has alpha spin or it doesn't have alpha spin. And we could take another direction vector, maybe going over like this, a beta direction, and then have another box that would test if it has beta spin. Okay? Well, quantum theory tells you about elementary particles. And so you can ask, well, what does quantum theory say about spin? Well, this is the way quantum theory talks to you. If you have a particular particle, you describe the particular particle, you can apply quantum theory and ask, does it have alpha spin? And quantum theory, as usual, will give you back probabilistic answers. So quantum theory might say, for example, it has alpha spin with probability 70%. And it doesn't have alpha spin with probability 30%. So that's the kind of answer you'll get from quantum theory. And if you can have a way of manufacturing particles that will give these, that will have those characteristics, 70% and 30%, what you'll find is that quantum theory is always right. Whatever it says seems to be always right, that if you had a bunch of particles like these, and you shoot them into this box, you'd find about 70% of them would turn the green light on, and about 30% would turn the red light on. So quantum theory seems to be right about everything it says. But it won't tell you if you have a particular particle whether or not it has alpha spin. It just doesn't tell you that. And Einstein's contention was, well, that tells you it's an incomplete theory, because it should either have alpha spin or not. Now, right off, it's not obvious that Einstein is right about that, because maybe this alpha spin, we don't know anything about what it is. Maybe the answer just arises in some spontaneous way inside that box. So what he wanted to do is devise an experiment that would show, in some way show, that the particle really does have a particular spin value before you test it. That's what he wanted to do, to say it really has a real spin value before you test it, so that quantum is incomplete. There's more detail that it's not telling. That was what he wanted to achieve. And what he did is he found, so to reiterate that, the question is, does every particle have a real inherent predetermined value, alpha spin value of either yes or no before it's tested? Just like does a particle have a real position before it's detected? That's the question. And if it does, then certainly quantum theory is incomplete because it doesn't give you that value. If it doesn't, then there could be no better theory that will predict the value of the spin since it doesn't have one. And Einstein argued that quantum theory is incomplete, that it must have a real inherent value. And so I want to describe to you the experiment that Einstein and his colleagues devised to demonstrate that there must be a real inherent value before it's tested. So what they did is they thought about, so this was Einstein, Podolsky, and Rosen in 1935. What they did is about electrons and positrons. Remember I said an electron and a positron. A positron is antimatter. It's an anti-electron. So if you have an electron and a positron and you bring them together, they will annihilate each other and just release energy, just turn into pure energy. And that's a fact. That really happens. And so what they imagined, they like to do thought experiments. So their thought experiment was to say, well, how about imagine that you concentrated a bunch of energy in one little spot in just the right way and reverse this reaction. So you concentrate a bunch of energy in one spot and out of it comes an electron and a positron. You just reverse that annihilation. It seems from our experience with physics that any reaction can be, under the right circumstances, reversed. So maybe there's a way to reverse this reaction and produce a pair, a positron and an electron that were formed together at the same moment out of energy. And so they described this pair, and they used quantum theory to describe it. They didn't have any way of actually physically doing this, but they could use what we know about elementary particles to describe what they would look like. And quantum theory would give a description of this kind of pair. They called it a singlet pair, and you'll see why that might be an appropriate name. What quantum theory says is that, well, first it says that for a singlet pair, if you choose any direction alpha whatsoever, that the probability that either one of those particles will have that spin is 1/2. Okay? For these particular kind of particles, quantum theory says that the probability that they will have alpha spin is 1/2, no matter which direction alpha you choose. In other words, as far as quantum theory is concerned, their spin is just about completely undetermined. That it just has a 50-50 chance of yes or no, no matter what test you do. But the interesting thing about these pairs that is useful for our purposes is that quantum theory also says that when you test these two particles, that the answers you get will be opposite. You'll always get either a yes here and a no here, or a no here and a yes here. So that these singlet pairs are really like a particle and its antiparticle. They're just exact opposites. And so for any spin test you want to do, you'll get opposite answers for the two particles. You'll get a yes on one and a no on the other. Well, they said, now, if that's true, what does that tell you? Look at this electron. Does it have an inherent spin value before you test it? Does it have a value of yes or no before you test it? Or does it arise when you test it? Well, you've got this pair, and you know this pair has opposite spin values. So you look at the electron and say, does it have a spin value of yes or no before you test it? Well, yes, it does, because look, if you want to know what it is without testing it, what do? You test the other one. And if you get a no on this one, you know that's yes. If you got a yes on this one, you know that's no, without testing this one at all. So these singlet pairs give an example where Einstein, Podolsky, and Rosen could say that definitely both particles have an inherent spin value before they're tested that quantum theory isn't telling us about. And therefore quantum theory is incomplete. And this argument looks very compelling. In fact, if you look at that, it's hard to imagine that could be wrong. That certainly these two particles must both have a spin value, a predetermined spin value, before you test them. Because you can know what it is by without testing it, by just testing the other one, since they have to be opposite. Well, when they showed this to the quantum theorists, again, the quantum theorists were sort of stubborn, and they said, oh, well, maybe you just have to get used to it. What's happening here? They said, well, you test the electron, and you get a yes. And just the same moment you test the electron to get a yes, that makes the positron no at that moment. Well, so what does that mean? There's some kind of strange communication between these two particles. But now, this experiment could be done by producing the two particles right here and shooting one to San Diego and one to New York and testing them there. And now you're saying the moment you test this one and you get a yes, this one automatically turns into a no. Now, what kind of nonsense is that? Well, the quantum theorist said, well, maybe you just have to get used to that. Well, Einstein said, no, that's just nonsense. But there was still some disagreement about this. And so, well, what Einstein did is they expressed this as a principle. They said every singlet pair has a real inherent predetermined alpha spin value of either yes or no before it's tested, because the other one has the opposite value. And since quantum theory doesn't give us this value, it's not a complete theory. And so what we should really be trying to do is we should be trying to find the complete theory that will tell you what the real spin value is and what the real location is of an electron. We shouldn't just settle for quantum theory because it's useful and it tells us what we really need to know. We should try to find the real truth. And that was his argument. The quantum theorists seem to be happy with having these two particles somehow, you do something to one and it does something to the other one instantaneously, although they're far apart. And they said that's just part of why quantum theory is strange. So, unfortunately, Einstein, this was in the 30s, Einstein continued to look at this, but he seemed to think he had settled it fairly well, and that people ought to look for a better theory, and there were people who did devise some other attempts, but they didn't come up with anything. And then Einstein passed on in the mid-50s, but in the 60s, a very interesting advance came with this. An experiment was devised by John Bell, which was intended to settle this once and for all. And look at the two possibilities. Einstein says that the particle has an inherent predetermined spin before it's tested, and quantum theory says no, it doesn't. And and just gives you these probabilities. And so what John Bell did is devised an experiment, or described an experiment, on these singlet pairs, which would have one outcome if Einstein was right, and the other outcome if the quantum theorists were right. And that's what we needed to settle it once and for all. And so I want to describe that experiment to you. And so this is what it involves. What we need is a deluxe spin tester. So instead of testing for just one direction, we're going to test for 3 directions. So the deluxe spin tester works like this. We have three directions now, and these 3 directions, alpha, beta, and gamma, are just like I've drawn them. They're 120 degrees apart. So there's 3 different spin directions. And what you can do now is you can turn a little dial or punch a button and pick any one you want, and it'll test a particle for that one. So if you want its beta spin direction, you just punch the beta button, and it'll give you an answer for beta, or for alpha, or for gamma. And so if Einstein is right, if the EPR principle is right, that the particle has a predetermined spin value before you test it, then each particle can be described as having an alpha value, a beta value, and a gamma value. So this particle might be yes for alpha, no for beta, and no for gamma. And let's see, there's several different possible types of particles then that you might have. You could have a particle that's no for alpha, no for beta, yes for gamma. And let's see, how many are there? 2 possibilities here, 2 here, and 2 here. So 2 times 2 times 2. There's 8 different possible types of particles, depending on those 3 directions. And so this experiment will involve looking at particles and asking which of these 8 types are they. Okay? So now I'm going to describe the Bell. Well, this was done by Bell and then actually simplified by David Merman, and in a way that still achieves what we want, and this is what I'm going to show you. So here is the experiment that they wanted to do. You take a singlet pair. Now, of course, we do have the little problem that we don't have any singlet pairs. So this is, again, a thought experiment. But it seems, just from what we generally know about things, that maybe singlet pairs arise somewhere, and maybe someday we'll find them and can do this. But if we did, here is the experiment that the Bell-Merman experiment. What they said is to take a singlet pair and take 2 of these deluxe spin testers, and what we're going to do is randomly choose alpha, beta, or gamma on this side, and randomly choose alpha, beta, gamma on that side. So you can think of having a little wheel that spins and chooses alpha, beta, or gamma. It's like a roulette wheel. So we randomly choose one here, maybe gamma, and randomly choose one here, maybe beta. And we get a yes or a no here, and a yes or a no here. So if we do this experiment, we're going to spin both of these, randomly pick one on each side, and get either a yes or no on each side. So we could either come up with yes, 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 no, no, yes, or no, no. So if we do this experiment, there's 4 possible outcomes. And now, the question they ask is this: what is the probability that the 2 outcomes will be different? Okay, so different would mean that the two outcomes are either yes, no, or they're no, yes. If the two outcomes are the same, that means it's yes, yes, or it's no, no. So the question they ask is, what is the probability that the two outcomes will be different? Now, this sounds like a funny question to ask, and it's not clear in advance why anyone would want to ask this. But, but bear with me, and let's see if we can answer it. What I'm going to tell you now, and I won't do this now, but I could do it if I had, if I could give a talk like this each night the rest of the week. You can, and this is part of what I found very fascinating about this, that the question is about probability. What's the probability they'll be different? Well, what's a good theory to use if you're interested in probabilities? Well, quantum theory. Quantum theory tells you about probabilities. So you could ask quantum theory, what is the probability they'll be different? Now, it turns out that that this to answer this requires very little quantum theory. And in fact, I've discussed this with physicists who didn't really believe it. But the quantum theory that you need to understand to do this calculation and find out what quantum theory says about this question is rather limited. You can just carve out a little piece of quantum theory and develop it from scratch and see how quantum theory would compute this probability and find out what the answer would be. So instead of asking you to come back 4 more nights, I'm going to tell you the answer. So the answer is that probability says that the quantum theory says that the probability of having the answers be different is exactly 1/2. Okay, half the time it'll be yes, no, no, yes, and half the time it'll be yes, yes, or no, no. That's what probability theory will tell you if you carve out that little piece of probability theory and do the calculation. So I have to ask you to take my word for that. But that's all I'm going to ask you to take my word for. Because what we can do now is we can actually do the calculation based on the EPR principle. The principle, which is what I would certainly expect if I didn't know anything about this, that each particle does either have a predetermined value for each spin test of yes or no. So if we just assume that, that means that each particle is of one of those 8 types. Either a yes, 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 no, yes, yes, no, no, and so forth. Each one has a predetermined spin value. Which is what Einstein insisted must be true. So let's do the calculation. So here we have so we have the singlet pair, the electron and the positron. And each one has an alpha spin value, a beta spin value, and a gamma spin value. And these columns here now give you the 8 possibilities for the electron. For the electron, it could be yes, 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 no, yes, no, yes, and so forth. There's 8 possibilities for the electron. But if you know what it is for the electron, then of course you automatically know what it is for the positron. If the electron is yes, is no, yes, yes, well, the positron for an alpha spin test will give the opposite answer as the electron. So it will give a yes. And for a beta test, it's got to give a no. And for a gamma test, it's got to give a no. So once you know the type of the electron, then the positron has to be just the opposite type. So that means that there's really just 8 types for the pair. Each pair is described by one of those 8 columns. And we'd like to know what is the probability that the outcomes will be different. And so we can just count them, because what we're going to do is look at each of these 8. Well, we won't have to look at all 8, but look at one of these and ask if for each of these types, what is the probability that they will be different? Well, so let's look at that type that I've boxed in here, where the electron gives us a no and 2 yeses. The positron gives us a yes and 2 no's. And now imagine you take that type of pair and you put it into this experiment. And let's see what the outcome could be. So, well, the outcome depends on which two experiments we do. So remember, we have alpha, beta, gamma on this side and alpha, beta, gamma on this side. And we're going to randomly choose one of these and one of these. So there's 3 choices on which experiment to do with the electron, and 3 choices for the positron. So there's, what, 3 times 3, 9 possible pairs of choices. We could test the electron, we could test them both for alpha. We could test the electron for alpha and the positron for beta, alpha, gamma, or the electron for beta and the positron for alpha, beta, 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 gamma, gamma, alpha, gamma, beta, gamma, gamma. So there's 9 possible pairs of tests that we could do. And remember, we agreed that we're going to pick them at random on both sides. So that means that each of those 9 has equal probability of being done. We'll pick them with equal probability. So look at each of those 9. Well, if we know which test we're doing, and we know which type of pair we're doing it to, then we know what the outcome will be. So let's just look at what the outcomes are. For this type, what will the outcome be? Let's see, so we look at each of the tests. And for each test, we can just say what the outcome is. We just read it out of this box. So for example, if we do a gamma test and an alpha test, so a gamma test on the electron and an alpha test on the positron, well, the gamma test on the electron gives us a yes, and the alpha test on the positron gives us a yes. So in this case, we do this test, we'll get a yes, yes. And we can just read out of this box for each test what it will be. And here they are. This test gives us a no, yes, a no, 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 yes, 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 no, and so forth. You just read them out of the box. So there's 9 tests. And now of those 9 tests, how many of them give us different answers? That was the question. What is the probability that the answers will be different? Well, you look at the 9 tests, how many of them give you a different answer? Well, this one, this one, this one, this one, and this one. So 5 of them do. So you're going to pick randomly one of these 9 tests, and out of the 9, 5 of them will give you different outcomes. The other 4 will give you the same outcome. Okay, so what is the probability that you're going to get different outcomes? Somebody? 5 ninths. Okay, 5 ninths. The probability is that you'll get different outcome 5 ninths of the time. That means that if you do this experiment 90 times, about 50 of them should give you different outcomes. Now that's for this type. But what about the other types? Well, if you look at these, each of these types has one particle is a yes and 2 no's, and the other particle is a no and 2 yeses, except the first type and the last type. So except for the first type and the last type, each one has 2 of one type and 2 of one answer and 1 of the other. So one side gives you a yes and 2 no's, the other a no and 2 yeses. And what that means is if you just repeat this process with any of these others, except the first and the last, it's going to come out the same. 5 out of 9 will be different. So you have to look at that for a minute, but well, maybe you take my word for it a little bit. It's really totally symmetric. So for any of these other, there are 6 of these that have a no and 2 yeses and a yes and 2 nos. And if you analyze them like this, you'll see that 5 out of the 9 will give you different outcomes. So that means if the type is any one of those inside 6, then the probability that you get different answers is 5/9. And now, what about if you have this first type? What's the probability that you'll get different answers? You do one of these with the electron, and one of those with the positron. What will the outcomes be? Well, what will the outcome for the electron be if you do one of those? It's going to be yes, whichever one you do. And for the positron, you're going to do one of these. It'll be no, whichever one you do. So you always get opposite outcomes. You always get a yes and a no. So if it's this first type, the probability is 1 that they'll be different. They'll always be different. Well, look at the last one. That's the same. They'll always be different. So we don't know how these different types are distributed among our singlet pairs, but what we know is that for 6 out of the 8, it will be 5/9, and for the other 2, it'll be 1. So what we can conclude is that for the whole thing, if we just try these pairs, the probability that we're going to get different answers is at least 5/9. If there are none of the first and last in it, then it will be exactly 5/9, otherwise it will be more, because those will always give us different answers. And so, so the probability, so for that one type, it's 5/9, and otherwise, and this is called Bell's theorem, published in 1964, that if the EPR principle is correct, then the probability that the outcomes are different is at least 5/9. Well, as I said before, if you do a little bit of quantum theory, you can use quantum theory to calculate the result for this one, and the probability that quantum theory gives you that they're different is 1/2. Well, so those are different outcomes. Quantum theory is now contradicted by the EPR principle with this experiment. And so what that says is that if we could just actually do this experiment, if we could actually produce these singlet pairs somehow, then we could do this experiment, and then we could find out who's right. You just produce a whole bunch of singlet pairs, and you perform this experiment a whole bunch of times, and you see, are they coming out different, close to half the time, or is it more than 5/9 of the time? And if you do enough of those experiments, then you could be very certain which one it was. Well, unfortunately, in 1964, they didn't have the technology to do this. Nobody knew how to produce these singlet pairs. It was a nice thought experiment, and it seemed reasonable that such things might exist, but nobody could produce them. Well, there was a big effort made, and in the late 80s, a lab in Paris actually did this. They actually produced the singlet pairs, and they tested it to see who was right. So who do you think is right? Well, turns out that quantum theory is right. They actually did it, and it came out that the probability is 1/2. Half the time they're different. And so this is now experimental proof that quantum theory is correct. This is experimental proof that the EPR principle is not correct. So these particles do not have a predetermined inherent spin before they're tested. And this was Einstein's famous remark about this when he argued about it. Der Gott spielt kein Würfel. God doesn't play dice. Well, it turns out that he does. The other thing that is very interesting, sort of serendipitous here about this experiment is that this means, if you go back to the original, Einstein's original experiment with the singlet pair, where they both, the pair is produced, they're shot far apart, and they're tested, and they have always have opposite spins, argued that meant they must have a predetermined spin before they're tested. Well, this shows that they don't. And what that means is that something really, really weird is going on. You can have these two particles, you generate them right here. You have a tester in San Diego and another one in New York, and you send them in opposite directions and test one of them, and instantaneously the other one takes on the opposite spin. And how that's happening, I guess, is still a mystery. Nobody has been able to say anything beyond that, except that, well, you just have to get used to it. So that's where we are. And so that's what I have to say.
We do have time for just a few questions now. You should know that tomorrow at 2 to 3 p.m. there is an open forum to ask them questions in the Lucas Engineering Building, room 119. Officially, that's students only, but should you show up and should there not be a lot of students with questions, we could probably let you slip one in. But if you'd like to ask the speaker any questions right now, please feel free. Yes, ma'am.
I'm not sure I understand how the quantum specifies that it's not predetermined. I understand why the Einstein view or the EPR says that that is a test for predetermination, but I don't understand why the quantum isn't predetermination.
Well, what happens is that if you assume that it is predetermined, then what happens is that you do this experiment, and the outcome of the experiment, if you assume it's predetermined, Bell's theorem says that the outcome of this experiment, that the probability of them being different is at least 5/9. So if you assume they're predetermined, that means that if you were to repeat this experiment over and over, that at least 5/9 of them would be different. And that experiment then was finally done and shown that that's not true. That only half of them are different. So what that tells us, the experiment that was actually done then tells us that the EPR principle, which says that they are predetermined, is wrong. And it also tells us that the quantum theoretic prediction in that case is correct. But I think particularly a principle of interest to us is that it says that the spin values are not predetermined. Because if you assume they are, you get a result that contradicts experiment. Does that answer? Good. Yes?
Is a choice of the number of spins that you're trying to measure influence that 5/9 number? Like if I chose 4 axes, since you said we didn't know what spin is,
Yes.
how do we know that 3 is a magic number for this test? Why not 4
You mean
or
the
5?
3, the alpha, beta, gamma?
Yeah.
The 3? Those are chosen very carefully to make this work at 120 degrees apart.
Okay.
In order to get something that what you want is just a contradiction, right? You assume that they are predetermined. And now what you'd like is just to do something that will contradict experiment. So conclude something from that that contradicts experiment. And so then those are chosen carefully to make that happen.
So if you chose them at 90 degrees apart, 4, then you would get half from Bell's theorem?
Well, you have to do the calculation, but maybe so. Yeah. All that matters is that there is a choice that contradicts experiment, and then you have a contradiction. Yes?
Has anybody built spin boxes in series that you can measure the same electron for spin?
Pardon?
Have they put a series of spin boxes?
Yes, that's a good question. If you have a spin box and you test something for alpha spin, and then send that same electron into another alpha spin box, you get the same answer. You get the same answer. And if you send it into a beta spin box, and beta is different from alpha, well, if you send it into a minus spin alpha spin box, you'll get the opposite answer. And if you send it into a beta spin box, where beta is some different angle, then that little bit of quantum theory that I said that you need to do this calculation will tell you exactly what the probability is if you send it through one and then another. So you can do that. Yes.
The mathematical model of quantum mechanics predicts these opposite spins for the positron and electron
Yes.
in a singular pair. But have there been any experiments to validate, because we don't really have singular pairs, individual singular pairs experiences.
Well, we do.
Validate that the spins are actually opposite on the
Yes.
If they're not.
There was, after all of this buildup over all these years, there was a lot of motivation to try to figure out how to do that. And then it was done. Yes.
Dr. Clark, quantum theory would predict that there's an influence after if you make the San Diego measurement or the New York measurement, the spin on the opposite particle, the spin of the other particle will be opposite. What does quantum theory say about making those measurements exactly simultaneously? Before one has a chance to, quote unquote, influence the other.
Yes, yes. Let's see. Well, they would say they were opposite. Quantum theory would say they're opposite, but you can't do it.
Yeah, I know you're
Right,
right.
you couldn't make them be exactly the same, simultaneous. In fact, you get in trouble with relativity because simultaneity isn't well defined in relativity. It has strange implications with relativity because if you try to test them at the same time, suppose you try to do it, so you test them at almost exactly the same time, okay? So one here and one here, that is close to the same time as you can. And you got a yes here and a no here. Now you do that, and while you're doing it, I run by you in this direction, okay? When I run by you in this direction, that brings time forward here and backward here. So I see this one tested first, and I say this one caused this one to switch. But while I do that, Ted runs by you in the other direction. And we have one of our usual disagreements.
Sorry I asked that question.
No, it's a good question. Yeah, we'll just have to sort it out. Yes.
Would there be a way of changing the spin on one? And if so, what would happen to the other?
Sure, make it one.
Change the spin on. Yeah, once you test it, then they are decoupled. So they aren't connected any longer. So now you could, if you do an alpha spin test on a particle, it will come out of the box. So say you get a no on it. It will come out of the box being a no particle. And now if you do another alpha spin test on it, it'll always give you no. So it'll be consistent once you've done it. So you've actually changed that particle. And now if you do, so if you had a pair like this, and you did the 2 spin tests, once you've done it, then one of them is now in an alpha yes state, and the other's in an alpha no state. Now if you do another test on this particle, say a beta test, it will come out of that test being a beta yes or beta no, but that won't influence this one because now they've been decoupled. Once they interact, they're no longer a single pair. Yes.
Sort of along that line, like what if you were to somehow mess with one of the particles before you make the observation? I guess what I'm getting at is I've just seen the calculation that happens, that, like if you take one of the particles and put it into a magnetic field, before you try measuring the spins, then what you can actually do is kind of take the singlet state and turn it into one of the triplet states and back again. It kind of oscillates. But that doesn't really, it's not like you can signal to the other guy though.
Yeah, right.
Is there any way of messing with the particle, one of the particles, before you go and measure it, you know, when it goes poof?
Yeah.
To somehow like send a signal to the other guy?
Yes, I don't know. They're very delicate. Part of the problem of doing this test is that if the particles interact with anything, then they change and now they're decoupled. And so when I say San Diego and New York, you probably couldn't quite do that. Though I think that there was a news article that somebody had the 2 particles that they got to go across the Danube and do it. So they're very delicate. So I don't know what messing with them you could do and get by with and still have them coupled. Yes?
Forgive me, I'm not a physics or a math student, and you've done a great job of making this very easy for me to understand. What is it about the testing, or is it the observation, that affects these particles so that they separate and that one is determined by the testing of the first?
That's a good question. I don't think anybody has an answer. All we know is what happens.
Or does that get into Schrodinger's cat?
Well, it's
The whole idea of observation.
yeah, it's strange like Schrodinger's cat. And all we know is that if you test one, then the other one has the opposite spin. And how that happens, to give any further better explanation of how that transpires, nobody's been able to do, but we know it's correct. And as I said, with that attempt to do it simultaneously, we can't even say that testing this one, we don't know which one caused the other one to switch, because it depends on your point of view as to which one happened first. So it's a good question, and we just don't know. Maybe we'll answer it someday. Yes?
I'm curious that you're saying that the alpha spin does not change when it goes through the first box. If you had a second box, it would stay in the no state.
That's right.
Doesn't that say it's predetermined in the distance between the 2 boxes?
Yeah, that one is. Mm-hmm.
Okay.
That one's predetermined, yes. It's predetermined, I mean, in that case it is. So,
So Einstein is
it's not
partially
saying,
right.
yeah, it's not saying that nothing's ever predetermined. But what Einstein wanted to say is that physics, the physical world is operating in a deterministic way. And so that would be an example where it is. But his intention is that it's always deterministic. And what is really novel for us and surprising, I think, is to really see that there are instances where the physical world, not anything subjective, but something really, I mean, nothing could be less subjective than an electron. It's, you know, the littlest thing you're going to find around. It operates in a way that's not deterministic. So what's interesting is that there are instances of the physical world not being deterministic. And that's interesting in terms of the whole history of that discussion.
players are out there. And one has an issue with perception, depth perception, or whatever kind of perception you want to say. Now, his brain is doing some kind of intuitive calculation, baseball is coming over, and both of them think they know where that ball is going to be, and they're about the same height, same reach, all of that. Is that why baseball players run into each other when they're trying to?
Well, I guess,
No, it's a serious.
yes,
it's a
yes.
serious
Yeah.
question.
Well, I guess if they had the same perception, then they'd run into each other, so maybe we hope they didn't. But,
I've often wondered about that, because
Yeah.
people do not see things the same.
yes,
There's inattentional blindness, there's physical blindness, there's
yes.
all these other things. And people don't see things the same, they don't perceive things the same, the sun gets in their eye. So why do these baseball players, I mean, because the physics would say, the ball's gonna be right there, like you said.
Mhm.
So why do they run into each other?
Yeah, it must be that they both have the same perception, that they both think it's coming down right here, and so they both go there. But of course, that has to do with people, and when you think of how much effort went into understanding how electrons are behaving, now you want to understand how people behave. I mean, I don't know how anyone does it.
Well, I'm just talking about the baseball, where it's going to land.
Yeah, yeah.